everyone, the topic of my paper is Rockburst probability early warning method based on integrated infrared temperature and acoustic emission parameters. And you can see the authors there, and you can also, I'm Manish Resta, roll number 2493250. This is the particular paper I was given to look into, and if you also want to look into these, then the references are there. Now, these are the outlines of my paper: introduction, methodology, data collection, results, discussions, and conclusion. I've just followed the outlines of the paper itself and haven't gone outside the paper. Now, introduction. You might say that I love explosions and stuff, but well, that is probably something that a rock burst would sound like. So when rocks explode under the ground, it's violent, it's sudden, and it can definitely threaten miners, tunnel engineers, or whoever professionals or laborers or equipments, machinery that are working under there. And even till date, these rock bursts are so unpredictable that developing a reliable early warning system has been a tough challenge, even though a lot of research is going on in this field, and there's still a need for real-time multi-parameter AI assisted prediction. So the purpose of this research was to develop a practical, accurate framework combining infrared heat signals and AE stress sounds to predict rock bursts more accurately. So according to the literature reviews, there have been different tools and parameters that have been used in previous researches, including microseismic parameters and so on and on, but they still haven't figured out something that would give you sufficient time for early warning. So basically, sticking to this particular experiment, they conducted true triaxial loading tests on granite blocks that were excavated from actual tunnels deep under the ground, and they conducted a total of 8 static driven and 8 dynamic triggered triaxial loading tests to collect the infrared and acoustic emission signals. You can see from this particular figure, which is in the research paper itself, that they made these blocks of size 50 mm by 50 mm by 100 mm each for the true triaxial loading tests. Then they set it up in a laboratory setup. I think I have a photo of it here. So this was the particular laboratory setup in which they had an infrared camera watching at the block. Then they had some AE sensors. These are basically like some mics, and they had the sample in between. Basically the steps that they followed, the flowchart of the whatever they had followed is over here. Like they conducted in step 1 2 triaxial loading and unloading rock burst tests. Then they did some analysis to determine the early warning indicators to check like if there are any precursors or any indicators right before a rock burst event that would somehow help them to give an early warning. So for that they did some time series prediction, warning thresholds were made, and then finally the early warning trigger was given. Now for this they used the sliding window segmentation approach, in which basically they were recording a video and an audio. So they break down the video and audio into small segments, and they analyze each of these segments to see the similarities between the consecutive segments, to see if there are any abnormal changes in them or abnormal fluctuations, maybe some drops or maybe some rises. And they used 3 different AI models: ELM, ESN, and LSTM for this research. And they used the cosine similarity approach or technique to figure out if there were any anomalies. And finally, they used the Bayesian theory to calculate rockburst probability. So you can also see here the experimental setup. They took a video, they processed the video by breaking them down into some temperature matrices. First they take a certain graphic, make it into grids, then develop a temperature matrix. Then they did some time series analysis, calculated some mean values, extreme values, and they figured out that there was some significant difference in extreme values right before a rockburst event. And they also used a technique called Gaussian filter to do some denoising. For data collection, like I said before, heat and sound were the 2 things they looked into. So if you look into this particular graph, they were applying a triaxial load. At the same time, they were taking some infrared temperature scans. At E1, E2, E3, and E4, you can see slowly the core temperature, the red indicates higher temperature, is increasing, and it reaches the highest density at E4, and you can see there's a significant rise in the average temperature over here. So basically IR captured the surface heat, which was a macroseismic energy, and acoustic emission captured internal stresses through microscopy, listening to some microscopic cracks. The main machine is as follows. There are description on the types of sensors they used. They used a 60 frames per second camera, a 2 megahertz sampling, and AE signals include amplitude, duration, frequency, IR processed with Gaussian filter, time series extraction, and they put the block around the holder, and they painted it black so that infrared could capture it more accurately. Talking about the results, so what did the data reveal? Well, the best indicators for early warning was found out to be infrared extreme temperature difference and acoustic emission amplitude fluctuation. You can see from this particular chart that the red line is the infrared average and the blue line is the infrared extreme difference. So right before a rockburst event, which is basically the end point over here, there's a significant rise in the difference between the minimum and the maximum temperature. So that was one thing. And also you can also see some AE magnitude fluctuations. The evolution of average temperature of the infrared image with static stress loading. So they conducted 2 types of tests. One was the static test, in which the load was gradually increased with time without any dynamic load, whereas in the dynamic loading, after a certain interval, around 0.25% of the initial load was supplied additionally as dynamic loading. And you can see these fluctuations basically mean that. They also took data of acoustic emissions, and they checked these 6 different parameters: peak, frequency, absolute, energy, amplitude, to figure out which of them would be a better indicator. So out of all these tests, they found out that LSTM outperformed ELM and ESN. Well, there's a small twist to this thing, because in terms of error, LSTM was the model that performed the least, or the worst performing model. But in terms of generalizability or like correlation, which it was the one that stood out the most. And there was maximum error in dynamic tests cosine similarity threshold, they set it to less than 0.98, which would trigger a warning. And similarly, Bayesian probability index used for risk classification. Early warnings achieved 2.1 to 41 seconds, which is a lot of time ahead of Rockbursts. So you can see that the model performance, like cross-validation parameters, you can see that this is it. Similarly, these are some of the charts from the paper, dynamic tests. This was the particular Rockburst index that we were talking about. It is basically the sum, the total probability of the warning state within a window times the probability of event A over the probability of. So this basically is where the probabilities of event 1 and B respectively occurring in the warning state within the window denotes the probability of both events occurring in the warning state within the same window. Predicting before it happens.